Assalamu alaikum. In this video, we will be introducing number systems. We are used in mathematics to use the decimal number system because it's a number that works very well with mathematical operations. But with computers, we have to use the binary system. With the current technology. So that's why we need to find a way to represent any decimal number using this binary system. And of course, also we will need a way to represent also characters using the binary system. So the binary system is based on two digits, so zeros and ones. These values are the only possible values that one bit can hold. So if we have a, a memory of 4 bits, for example, here, the only numbers that you can write here, they go from 0000 to then 0001, 0010 until 1111. Okay, we'll talk later about how many um, uh, combinations we have here. And then we have also the octal system. The octal system is based on 8 digits, which are the digits from 0 to 7, and also the hexadecimal system, which goes from 0 to 15. So because we don't have digits that represent the numbers from 10 to 15, that's why we use the letters from A to F. So A represents 10, so this is 10, this is 11, this is 12 until 15. Okay, so now we will look at how these systems work. So when we used to use the decimal number system here, we call the number 10 is called the radix. Radix is the number of digits that are allowed in this system. So here, when we talk about the decimal number system, we call we are talking about the number system of that is using the radix 10 or the number of base 10. So when we use the base 10, we have symbols from 0 to 10 minus 1. So that's why when we have radix n, we have digits from 0 to n minus 1. So for numbers bigger than 10, we will need to add positions, additional positions. So this is what we call a positional system. So the first position is here. It's the position of the units. Here you have 10 to the power of 0. So these are the units. 10 to the power of 0 is 1. So any value that will go here will have a weight of 10 to the power of 0. So if we have the number, for example, 7 here, 3, for example, here, and 4 here, this has the weight 10. So this, the real value of this digit here is 7 multiplied by 10 to the power of 0. The real value of this 3 here, because it is in this position here, it has the value of 3 multiplied by 10 to the power of 1, which is 30. And this number here have its real value is 4 multiplied by 10 to the power of 2, which is 100. So this represents 400. And then we have, so this is for the integer part. So this is the integer part. And this is the fractional part. Fractional. Of course, we have the dot here that separates the two parts. So here, any number that goes at this position, at the right of the dot. So here, for example, if you have 5, 6, 8, this 5, the real value of this 5 is 5 multiplied by 10 to the power of minus 1, which is 5 divided by 10. The 6 has the value of 6 multiplied by 10 to the power of minus 2, which is 6 divided by 100, which is 0.06, and so on. So the real value of 8 is 8 multiplied by 10 to the power of minus 3, which is 0.008, and so on. So this is a positional system, and all the other systems, they also um, uh, are positional systems, which mean that they also are using uh, uh, these positions to represent weights. So each number will have a weight according to the position where it is placed. So the number that is represented here, if you want to get the real value, so the value um, is the sum of any digit that is here. So 1936.25. So the one is at the fourth position. So the one has the weight of 10 to the power of 3, and so on. So this is the general rule here expressed in this slide. So the number, the real value of any number, if we want to transform it to the decimal representation of the number. So if we have a number expressed with radix r, so let's say, for example, radix 2 as an example. So if we want to get the real value of the number, we need to sum from 0 to n minus 1. So 0 to n minus 1, this is the integer part of the number, multiplied by r to the power of I. So for the first element here, the value of this element here is ai, which is a0, multiplied by r to the power of 0. So if r is 2, so this will be the value of the digit that is here. For example, of course, if we are using radix 2, for example, we will only have zeros or ones. So it will be 0 or 1 multiplied by 2 to the power of the position, which is 0. So it will be 1. And then also we need to add all the elements that are on the fractional part. So here we need to sum from minus m to minus 1. Minus m is the last fractional digit until minus 1. And here we have to multiply the same thing, the digit, the value of the digit itself that is here, multiplied by the weight of this digit. So this is a table that represents the some numbers using in the decimal and the binary basis. So here, for example, we have radix 2, we have radix 4 here. So in radix 10, we have digits from 0 to 9, in binary from 0 to 1, and then for the powers of the radix, they represent the weight of the digit at that position. So for example, the element that will be in position, this is the fourth position because we start counting at 0. So the number that will be at this position here will have a weight of 1000 for the decimal numbers and 8 for the binary numbers. So we'll take some examples to explain this. So for example, for the binary number system, we will use exactly the same positional system as in the decimal system. So let's look directly to the examples. So for example, 000 is if this is in binary, this represents 0 multiplied by 2 to the power of 3 plus 0 multiplied by 2 to the power of 2 plus 0 multiplied by 2 to the power of 1 plus 0 multiplied by 2 to the power of 0. Okay, of course we do not, in this case, we do not need to do all this to get the real value in base 10 because everything is 0, but this is how we represent 0 in 4 bits using the binary system. So So the only digits that are allowed are zeros and ones. So now let's look at the conversion from binary to decimal, and then we'll look at the opposite conversion. So here, uh, the binary to decimal conversion is just the explicit expression of the positional values. So we just take the positional values, so 101 in base 2. If we want to get the real value in decimal, I mean the representation of this number in the decimal system, here we'll take the first one here, which is at the position 0. So this the value of 1, the value of this one here is 1 multiplied by the weight of this position, which is 2 to the power of 0. So then we have 0 multiplied by 2 to the power of 1, and then 1 multiplied by 2 to the power of 2. So 2 to the power of 2 is 4, 2 to the power of 1 is 2, and 2 to the power of 0 is 1. is 1. So this will give us 5. So this is a very straightforward transformation. So for example, here we have another example. So what is 100111000 in decimal? So here we have 100111000. So this number here is the number at position 0. So this has the weight of 2 to the power of 0. This has the weight of 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and finally 2 to the power of 7. So this will give us 0. So let's start from this bit here, which is the least significant bit. This is called the least significant bit, and this is called the most significant bit. So we start by the least significant bit. This will give us 0 multiplied by 2 to the power of 0 plus 0 multiplied by 2 to the power of 1 plus 1 2 to the power of 2 plus 1 2 to the power of 3 plus 1 multiplied by 2 to the power of 4. Then we have zeros plus 0 multiplied by 2 to the power of 5 plus 0 multiplied by 2 to the power of 6 plus finally 1 multiplied by 2 to the power of 7. So the zeros are directly cancelled. So it's of course easier to only write the ones here. So 1 multiplied by 4 is 4, plus 1 multiplied by 8 is 8, plus 1 multiplied by 16 is 16. So 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 6 is 64, and 2 to the power of 7 is 128. So we still have 128. So we just need to make the computation. So this is 20, 120, 148 plus 8, 156. So this is the conversion from decimal from binary to decimal. And in the next video, we'll look at other conversions.